Good afternoon, everyone, and welcome to our webinar today. My name is Ruchika Diora, and I'm the Program Director for the Center for New Energy Technologies. I'd like to acknowledge the traditional owners of country throughout Australia, where the hosts of this webinar are, and recognize continuing connections to land, waters, and communities, and pay our respects to Aboriginal and Torres Strait Island cultures and to elders past, present, and emerging. This is such an exciting webinar. It's the culmination of 2 years of research into a topic that is really present and quite relevant for most low voltage distribution network service providers. And that's around how do we enable better understanding of integration of dynamic operating envelopes as a key enabler for more distributed energy resources on the electricity grid. These envelopes are contractual and operational limits that define how much electricity a customer or consumer can import or export to the electricity grid using their DER, such as rooftop solar, electric vehicles, or other storage devices. And in most cases, these limits tend to be fixed right now, and they're typically fixed at conservative levels that are designed to protect network assets and consumer devices and maintain compliance and regulatory obligations. But instead of static export constraints, dynamic operating envelopes can allow for more export at time of days when the system can actually handle export load and only constrains exports when there's an actual danger to the assets on the network. But for this to occur, we know that DNSPs need really detailed visibility into low voltage networks. And in the past, this has required electric models of LV circuits that include impedances, phase connectivity, nodal placement, really complex, time-consuming, and oftentimes inaccurate modeling of these low-voltage networks. That's what's so exciting about this project. It provides the technical foundations and the specifications through computing processes and algorithms for DNSPs to estimate the maximum power exports or imports of individual customers without having to go through that time-consuming electrical modeling of low-voltage circuits, hence the model-free element of the project, instead using the AMI data that we have here in Victoria. So the project model-free operating envelopes at NIMI level has successfully demonstrated that it's possible to utilize this historic smart meter data and capture the real-world physics of LV networks to create electrical model-free approaches to calculating what flexible export limits could look like. And this approach represents an accurate, cheap, and extremely fast alternative to traditional model-driven approaches, therefore enabling DNSPs to bypass these costly, time-consuming, and sometimes error-prone processes of producing and validating electrical models. Today, we're going to hear from researchers Nando, Ochoa, and Vincenzo Zillmann to present their model-free approach to calculating flexible exports limits developed throughout this 2-year project, and they'll demonstrate the application using actual anonymized smart meter data from hundreds of Victorian customers, thus highlighting the benefits, the considerations, and the effectiveness, even in cases where there's only partial smart meter data availability. Again, I cannot reinforce how excited we are about this particular project. C4Net and our partner DNSPs would really like to thank Nando and Vincenzo and the entire team from University of Melbourne for their research and insights into this piece of work. Their deep engagement with industry and the project iterations based on the quality and availability of data demonstrate the power of this world-class research, and is exactly why C4Net was formed. So we're really thrilled to hear from the project team today, and I'll pass it over to Nando and Vincenzo. Thank you.
You're on mute, Nando, sorry.
There you go. Thank you very much, Chika, and thank you very much, everyone, for joining us today. Good morning, good afternoon, good evening, wherever in the world you are. And for my fellow Australians, well, good afternoon, good morning for some, actually, as a matter of fact. So today we have the conclusion, the final webinar of this 2-year project. We're very excited to share in just 40 or 50 minutes, what we thought were the most important aspects of this project. So before we start, just to let you know that there will be time for Q&A. So please do use the Q&A box as you wish. Put your questions there as they pop up. And I will go through all of them, time allowing, of course. And of course, you know that the webinar is recorded, so you will get the slides and everything. So before I start, of course, Vincenzo is, I call him Vinny, everyone calls him Vinny as well. He's joining us today. He will be presenting these slides with me, but I would like to thank also, you know, our collaborators, Tansu and Chris. They are part of the university, and they were key as well in making sure that the machine learning aspects were up to scratch for this particular project. All right, just following what Chica mentioned in terms of the acknowledgement country, I also would like to acknowledge country and particularly the traditional owners of the lands. We are today here at the University of Melbourne, and in Parkville right now, but all the University of Melbourne campuses. We pay our respects to their elders past, present, and emerging. All right, so the team, as I was mentioning, well, it includes Stan, Swan, Chris, Vinny, and myself. We had other researchers as well that at some point, because was a 2-year project, were involved. Thanks, Dylan, he's right now working for ICON, and different other researchers that in one way or another help us as well. Michael Liu, we have Angela as well, and Ishan, part of my team as well. Now, in terms of the outline, in the next 35, 40 minutes, hopefully, we will go through the different topics that I'm outlining here. So first and foremost, I want to explain what flexible export limits is or are. In a sense, as Chica was mentioning, what we really want is to calculate values, operational values that actually tell people this is how much you can export, or in the future, perhaps even import. And this is very important because we have also a lot of distributed energy resources, particularly in Australia, and well, the networks are really hitting their capacity, not just in terms of necessarily the amps that they can withhold, you know, the kVA, the capacity in terms of the power, but also the voltages, and that brings a lot of challenges, particularly in the residential areas, the low voltage networks. I will explain a little bit more about them, and then we will move into our model-free approach. So what we're doing, I'm not going to get into extreme details. There's plenty of literature that we have produced, reports and papers, and they are all publicly available. But then we will get into the case studies, really, you know, okay, how does it look like? What sort of results will we get? That's the part 3 that Vincenzo will go through, the model-free flexible export limits. And we will show you, know, the capabilities of these machine learning techniques that we're using just with the smart meter data. And what's next is really just highlighting the fact that, well, this is just a building block within a much larger advanced platform that needs to be put together by distribution companies, not just in Australia, but around the world, if they wish to actually enable flexible export limits or operating envelopes in general. But also, it's not just about flexible export limits. There are many other things that we can do with this model-free approach. Hosting capacity is one of that, and I will show some results as well, and then some key remarks. So let's start first with flexible export limits. For me, it's very important to have everyone on the same page so we know what we're talking about. Some of you that might be familiar with some of the work that we have done for Project Edge, a project that concluded recently and was funded by Arena and Austin Services, IEMO, and other companies. The University of Melbourne was involved, and we were really calculating operating envelopes with models, electrical models, and that was including imports and exports. But here right now, we're going to focus only on exports, and there's a reason why. First of all, as I was mentioning, we have a lot of photovoltaics in Australia, and right now people have a standard offer depending on where they're located, you know, and electrically located, where you're in a rural area or in a urban area. The standard offer is around 5 kilowatts per phase in terms of what you can export. You can have a larger system, sure, but what you can export is 5 kilowatts. So what people actually end up doing is putting a PV inverter no larger than 5 kVA, because that's the easier way. Or if they do it, they put some export limits there that are fixed, not to exceed always the 5 kilowatts. The reality is that depending on where you are, this value can be much less. 3.5 in square areas, single wire array return, so rural areas. In certain areas where there's a lot of photovoltaic, can be 2 kilowatts, or in certain cases can be 0, nothing. Now you can still use it locally, of course, for your own needs, for your own electricity demand, you know, to cover it. But in terms of exports, in certain cases, can be very, very little. Now, why is this bad? Because of course, it to some extent might discourage PV adoption, and that's kind of not aligned with what we want to do in terms of the decarbonization of the electricity system. It also discourages potential services that aggregators might want to sort of enable by collating all these distributed energy resources, not just solar photovoltaics, but also batteries and electric vehicles, things like that. So it discourages that. And in general, it's just inefficient use of the poles and wires. Why? Because actually those values that the distribution companies are coming up with, they're not necessarily wrong, but they are for that worst case scenario, that particular day that is super sunny and the demand is very little, and suddenly, we need to protect the network. So those limits are okay, but the thing is that during the year, there are many more hours where that limit is just way too conservative. So you can actually make the most of the poles and wires at other times. So because of that, in Australia, the Australian Energy Regulator has already decided that distribution companies in their next regulatory period, they will be able to offer what we call flexible export limits. They are focusing on the exports right now because that's the largest problem, right, in Australia. But eventually, the idea, the concept is something that might also involve imports. Think of electric vehicles, right? So the idea is that instead of having these fixed limits throughout the day that we all have, all our houses have, we have a fuse there. We cannot go beyond that, otherwise our fuse opens. Or the flexible or the fixed limits, just because of the exports that you are being told, by the distribution company. Instead of having that fixed value, then we move to something that is changing in time. It's time varying. So we also call it operating envelopes or dynamic operating envelopes. But right now, what the AER, the Australian Energy Regulator, has described as something that can be done is the export limits. So that's what we are focusing today on, the export limits. We're going to share the slides and all the links, for you to read more about this. And the rules are going to be available, right? So how this would work is what I'm going to explain in the next slide, but I wanted to emphasize that this is a world first. There's nowhere in the world that is something like this is actually happening. And that is pretty exciting. Now, how would this work? So, well, someone has to calculate these flexible export limits because they are time varying, right? And they change in time. And then once they are calculated in advance, perhaps, or in real time, they need to be broadcast to the photovoltaic inverter or to the meter connection point, right? To the meter, actually, or to aggregators themselves that are actually managing on behalf of the end user the corresponding devices. So they need to be broadcast eventually. And then, of course, the corresponding PV inverter or the aggregator, that is managing everything there behind the meter, decides to act according to this limit. And with that, well, we make sure that distributed energy resources, not just photovoltaics, everything, will use the available capacity at that moment in time, if they wish to as well, of course. We can enable bottom-up services for aggregators, and we ensure, very importantly, that the poles and wires are okay. Not just the assets are okay, but also the voltages. They are very important for us not to have, our PV inverters tripping on some other power quality issues. All right. Now, because these are time-varying export limits, it means that we need to calculate them, some information. First of all, we are going to calculate it only for those customers that are flexible, those that opted for this type of arrangement. The other customers, the fixed customers, they continue to have their own limits. Now, you need information. You need information so you can actually define what is going to be that export limit for these flexible customers in the next 5 minutes. Or if you do it in advance, you will need forecasts as well, which of course brings more challenges. You need to consider the voltages at the customer connection points of what would happen, if these exports are higher and higher, higher. And you need to also consider what are the effects on the corresponding assets, right? The conductors and the transformers, because all of this varies throughout the day. And this depends not just on what people are going to export, your flexible customers, but also those that are not flexible. They are going to do something. So how you need to cater for them as well. It means that we really need a lot of data. And conventionally, we will think, well, we need a lot of measurements and network models. Actually, that's what we did in Project Edge, which I'm trying to describe there with those graphs on the right-hand side. So that's for exports and imports. And what we can see there is that this is limits that have been imposed per customer. Those are the different colors. And those customers have the same proportion because this is what we call an equal allocation. More on that later. But this is just an illustration of what the operating envelopes will be. And if you think of flexible experiments, it will be just the export part. And the idea is that it changes in time because, of course, the conditions of the network and how people are using it. At night, there's no photovoltaics, right? It really matters because then it's according to that state that we will be allowed to calculate larger or smaller export limits. But if you don't have a network model, then what can you do? Well, you end up with simplifications. And of course, this would be much, much less accurate. Now, in an ideal situation, what would you do? Well, you would actually use a lot of data, right? Your smart meter data, perhaps as well, likely transformer measurements, all right? Your distribution transformer. And you would define scenarios well to check, right? So photovoltaics exporting more, or the batteries, or whatever it is. Then you would use your electrical model in the residential part. The low voltage network is a three-phase low voltage network. Here in Australia is 400 volts line to line, so 230 volts line to neutral. And then when you run power flows, you explore different cases to check the corresponding voltages and the utilization of the assets for all the different cases, that particular scenario. And then if everything is fine, then you explore another export value and another export value until you get to the limits, right? When you hit a voltage constraint or an asset is overutilized, right? So that's something that you don't want. Now, that is what you would like to do ideally, right? But to achieve that, it means that you need to produce a low voltage network models. And that is something that we do not have in most cases. And if we do have them, if the distribution companies do have them, they are normally not necessarily very accurate, because the phase grouping is not known. Impedances sometimes are just basic estimations. The topology is not necessarily confirmed. So there are a lot of challenges. So you cannot trust a power flow run with those electrical models. But I mean, you can actually still validate them, but it's extremely time consuming and expensive to get it right. So what if we could check voltages on assets without electrical models? And that's the whole point of this model-free approach. Now, as I mentioned earlier, there's a lot of material and content that is freely available. All the links are going to be made available to you all, but we will try to explain this just in a very high level. All the material is available in the project website, all right? And this is just a snapshot of the project website. And again, as I mentioned earlier, well, you will have all the links for you to really go through the material yourself. So the idea is that in that block where we had our power flow, right, you will replace it with model-free voltage calculations and asset utilization calculations. Now, how do we do this? Well, what we are proposing here, and perhaps there are other regression methods, machine learning methods, but what we used was neural networks. And we were able to demonstrate that, as Chica correctly mentioned, that you can actually produce with smart meter data, and not a lot of it, actually, just 3 weeks, 5-minute resolution, P, Q, and V. You can actually extract the physics of the network, the low voltage network, all right? And with that, you can then infer the corresponding voltages for any what-if scenario. Because as any power flow, if you have P and Q, then you produce voltages. Same thing with the neural network. If you have the P and Q of that scenario, I can tell you the voltages, and then I can check where these export limits are hitting, the voltage limit, and then that's how I calculate. Now, of course, it's not just about voltages. You also need to calculate what happens to the transformer. And if you don't have the topology and electrical models, well, there will be some assumptions that you need to make. And for that, we use the net demands of individuals, the smart meters, and aggregate it as well to check the transformer. And with that, that is the proxy of the power flows. We are not going to use power flows. We're going to use just data and very clever machine learning techniques. Now, the idea here behind is that by doing so, we can remove the quite high cost and time associated with the production of electrical models, right? Now, interestingly as well, the moment you have a neural network that is produced actually in a matter of minutes or hours at most, depending on where you parallelize the computing or not. Once you have it, then you can actually run the calculations much, much faster than power flows, because power flows are iterative. So there are multiple benefits. Now, how do we do this? So there are 2 stages, okay? The first stage is what we call the development, is the production of the neural network, right? So you have your smart meter data that needs to be processed, because, I mean, real data always has some little issues here and there, so you need to be careful with that. And once you process it, you then produce a corresponding neural network, and I will explain that in the next slides. Once you produce a neural network, it means that now you're able to calculate voltages as a function of active and reactive power of those customers. And you will find the voltage of those customers for those particular scenarios. And that's what we are going to use it. Now, the applications are many. Right now, today, what we are focusing on are flexible export limits. But this can also be done for hosting capacity, connection requests, and many other things that I will discuss in the summary. So once you define that scenario to check, you define the active and reactive power. So in terms of, demand or, generation, then you will calculate the voltages within the network. You will use our heuristics to assess, how the assets are being utilized. And then you will check and produce, the corresponding export limits. You will check different scenarios. And the same process will apply for hosting capacity or connection requests. Now, getting into a little bit more of details of how we process the data, which is the first stage, there are multiple steps, but in a nutshell, what we need to ensure is that we remove instances of data that are missing. So we need every time step to have data, all right? Sometimes it's missing. It happens in real data, in real databases, because of issues, with comms or issues, with the smart meter or different other issues. So we need to make sure that all the points, for the customers have smart meter data. So you remove those that don't have for whatever reason. Even if one customer says have, they remove it. Then you remove also invalid and erroneous instances. Sometimes voltages, I mentioned that here in Australia, single phase customers will have voltages around 230 volts, right? Yeah, there are limits for sure because the voltages fluctuate, but actually 100 volts is something that is unexpected for steady state situations, right? So you will remove those weird voltages. They can happen actually, by the way, not just voltages, but also currents, etc. So you remove the weird stuff that can happen. And also you need to remove what we call abnormal behaviors, all right? So let's suppose that there's a house that is not occupied because sometimes it's construction time, right? And the smart meter might record, 0 or very tiny values. But then suddenly you want to do a flexible export limit for this customer that you haven't seen nothing really normal, then of course the neural network will not work properly. So you need to remove those abnormal sequences as well. So all in all, this processing will allow you to put together the training data set. And very important for us, this is just 3 weeks of data, 5-minute resolution. Around 3 weeks, it depends, on certain cases, but it's very, very little. And of course, this data should correspond to a moment in time, a period in time where the low voltage network hasn't changed topologically. It can happen throughout a year, the low voltage network changes, but in this case, in 3 weeks, is very unlikely. So you just pick as a distribution company, what is the period that it hasn't changed. Apart from that, all good. Now, then we move on to the neural network selection, the production of the neural network. Now, we have a lot of documentation about this, but in a nutshell, we already have what we call a recipe. And the recipe is a combination of 2 aspects. The corresponding, what we call the fixed hyperparameters, they're in the first table that you're seeing there. So for instance, the number of inputs, it will be twice the number of customers because it's P and Q per customer. And then the output is the number of customers, which are going to be the voltage. Now, the C that we refer to customers, actually for the neural network means a single phase customer. So if it's 3-phase, there are like 3 customers. It's the same customer, but we call it, individual there. So that's how it is being produced. So if you have a few 3-phase customers or 2-phase customers, then well, they create more customers in inverted commas. Now you have in step 6 the remaining hyperparameters that you need to define it as well. So it means that we have a big search space that we have actually nailed it down to those values there that you see in the second table. And it creates multiple combinations of all these cases. And of course, requires some time, but it's not a lot. So this recipe allows you to then produce a search space from which you're going to extract the best neural networks. Now, in step 7, because we're talking about 3 weeks, what you do is you also do a k-fold validation where you actually use 1 week in these 3 weeks. Now, this is a process to, again, refine the neural networks. But eventually what you get is all the hyperparameters for 10 neural networks, and then you just check again what is the best of them based on their error. In this case, a root mean square error. And then with that, you have your final neural network, and that's ready. And this can be produced in hours, depending if it's just a single basic computer. And when I say hours, it's no more than 3 hours, really. That's a lot already. But if you start parallelizing this and you have a very good computer, we are talking about less than an hour, even minutes. So this is something that we have already reported. This is in our reports, in our papers. But now let me show you some of the results. So final, that's a few slides, but finally, what you have is the model-free voltage calculations. So you have a function there, which is the neural network, that is able to calculate voltages for those customers for a given scenario of P and Q. All right, so now we can check the voltages. However, that doesn't finish there because we still are talking about export limits, right? So let me show you in the next slide how we calculate that, and then we'll get to the results. Just to remind you, we have done this with open source software. We have used TensorFlow and Keras, of course, and all of this in Python. Now, the flexible export limits then is the whole sort of process by which we calculate the flexible export limits, because so far I was explaining the neural network, right? Now, the flexible export limits is an exploration, right? An exploration that could be done with power flows, for instance, as well. But as I was explaining, well, for power flows, you need electrical models. We don't have the electrical models. You cannot do it, right? You can do these calculations also just assuming things, just based on the transformer, for instance. But of course, the values are not going to be that great. But that's a starting point nonetheless for distribution companies. If we want to get more sophisticated, perhaps we can do something like the model free. And how would you do it? Well, you will have your inputs, all right, which is for that particular scenario that you are going to assess the exports, all right? So you define what is the net demand of those non-flexible customers, the demand, the reactive power of the flexible customers, that you are going to consider for that scenario, your network constraints, so for the voltages, the assets, etc. In terms of the algorithm, then you start really evaluating the corresponding flexible limits by assessing for different sets of flexible export limits, what happens to the voltages and what happens to the assets. And then you start increasing the exports or decreasing them, depending on where you start, from larger exports or from no exports. And by doing this check, you will assess what is the optimal point, if you wish. And then finally, you find the flexible limits. Now, for those of you that are wondering, how do we do it, in terms of the network constraints? So the voltage limits, of course, they are checked with the neural network. That's the whole point of what I was trying to explain with the neural network. And in terms of asset utilization, what we do, because we don't have the topology, the idea is that you do all these, just with the smart meter data. Well, we know what is the maximum export that you can have physically, all right, per customer, because it depends on the customer connection point, the service cable, right, or the fuse if you want. We also know what is the size of the conductor that is departing from the transformer, so we can use that as well as a proxy of what is going to happen in the rest of the network. And we also can check that distribution transformer because we have the aggregated of the smart meters that we have available. So all of these can be used, but of course there are refinements that can be done if you know the phase groups that can actually be done as well with some machine learning techniques. Now that is the method, and then now let's get into the results. So let me just share the remote control with Vinny. And Vinny, you should be able now to show us the results.
Yeah, perfect. All right, so as Nando was saying, I brought to you the case study for this. So we are going to go through the production of the neural network, and then we're going to use this neural network to calculate flexible export limits. So let me test the control. There you go. Oh, sorry, a bit slow here. All right, perfect. So the case study that we wrote today is a low voltage network. As Nando was mentioned, these low voltage networks are Australian type. So they are three-phase low voltage network and 230 volts line to neutral. The low voltage network that we use for this case study, we call it Gemena Substation B, which is the largest low voltage network that we assess throughout this project. So in general terms, this is a 4 low voltage circuits, low voltage network, which originally has more than 150 customers. After this, the first step that we do is this data processing that Nando was explaining. So after this process, we remove some customers that do not present normal demand behavior. So after this process, we end up with a total of 146 customers. As well, this low voltage network accounts for 14% of PV penetration, and we use 5-minute resolution smart meter data. It means customers' active and reactive powers, as well as voltage magnitude. So in terms of the neural network training and selection, we are going to use 3 weeks of historical smart meter data to produce the neural network. It means that we're going to use these 3 weeks to go through the entire process that Nando was mentioning before. And once we obtain the best neural network, we are going to use it to calculate flexible export limit. So the first objective in here is going to be to produce a single neural network for all low voltage circuits in this low voltage network, and then we're going to use this neural network to calculate flexible export limits. So in terms of the training data that we use, which is the data that we use to produce the neural network, this data corresponds to the months of November, December, which in this side of the world is the end of spring, start of summer. And what we can see in here, well, in the upper plot, you can see the active power. In the middle one, you can see reactive power. And in the lower one, you can see voltage. So in terms of active power, as I was saying, we have a 14% of PV penetration. So we can see that there is some PV injections. In terms of reactive power, we can see that we have both positive and negative values. So we can say that we have capacitor and inductive power factors throughout the day. Finally, in terms of voltages, we can see that this low voltage network is already constrained, as is reaching in some parts of the training data set, is breaching the voltage upper statutory limit, which for Australia is 253 volts. So we use all these 3 weeks of smart meter data at 5-minute resolution to produce our neural network. So in terms of the hyperparameters and the structure of this neural network, well, there are many hyperparameters that are fixed, as Nando was saying. So for instance, the number of inputs is going to be twice the per phase number of customers, which is essentially customers active and reactive powers. The number of outputs is going to be customer voltages, again, per phase, that what we call C. Then we have some hyperparameters that are given by the nature of the problem, such as the error function, the activation function at the output layer, and so on. Important in here is to highlight that we use L2 regularization to enhance the extrapolation capabilities of our approach, which is really important for all the applications. Let's say flexible expert limit, which is all about pushing the limits of our neural network. Then we have this hyperparameter selection, which we do through a k-fold cross-validation, in which we select the best hyperparameters for this particular low voltage network. So in here, we select the number of neurons, the learning rate, the regularization factor, the number of epochs, and so on. Once we have decided these hyperparameters that are the most suitable for this low voltage network, we're going to train 10 neural networks from scratch using the entire training dataset. And we're going to select the best one based on its root mean square error during training. The one with the lowest root mean square error during training is going to correspond to the final neural network, which is all ready to calculate voltages. So what we're going to do then is that we're going to assess the accuracy of our neural network. For this, we're going to take another 3 weeks of data, which hasn't been seen by the neural network. And this data corresponds to the period of January, March. So it's fully summer in here. So again, in the upper plot, you can see active power. In the middle, you can see reactive power. And in the lower part, you can see voltage. So again, we can see that we have PV generation. We see that we have capacity of inductive power factors. And again, we can see that our low voltage network is already constrained in terms of voltages as we are reaching the upper limit. So how accurate is this? Well, in terms of numbers, we can see that we obtain in the test set, we obtain an average deviation of less than 0.6 volts, which is really, really accurate. And we can see that we obtain a maximum deviation that can be high. So right here, what we are presenting is up to 9 volts around. So in the left plot, what we are plotting here is a scatter plot, which the y-axis corresponds to the calculated voltages, whereas the x-axis corresponds to the actual voltage values. So the idea in here is that if everything were perfect, all the values will be aligned with the identity line, which we are plotting in dashed gray. But of course, as smart meters has noise and etc., and it's not perfect, we always going to have a little spread around this. But what is important in here is that we can see that our calculations resemble this identity line, which means that we are accurately capturing the underlying relationships of our low voltage network. In the right part, what you can see is a violin plot that corresponds to all the deviation for all customers at all instances. What is important to highlight in here is that we can see that although we have a maximum deviation that can be high, this occurs only in a reduced number of instances. For instance, we can stress that the yellow part, which represents 50% of deviations, is really, really constrained to a really small value, so below 0.5 volts, 0.4 volts. Yes, 0.4 volts. So here, what we are presenting are the time series results. So what you can see in here, well, the colored regions are to represent the difference between the maximum and the minimum value in each instant. In black, you are seeing the test actual voltage values, which correspond to the real smart meter values. Whereas in purple, what you can see are the calculations done by our neural network. And what you can see is that we obtain accurate voltage calculations. So for instance, our neural network is able to capture all the voltage rise and the big voltage drops that you can see throughout these 3 weeks of data of the test set. So we can see that our neural network has accurately captured the physics of this low voltage network. The control stuff is, there you go. So now that we have proved that our neural network has captured the physics, let's use the neural network to calculate flexible expert limits. So for this, we're going to use, of course, the same low voltage network, and we are going to use one day or one summer day with high PV injections to calculate flexible expert limits. We're going to consider all single phase customers with PV system as flexible customers, and we are going to consider perfect forecast, as forecast is outside of the scope of this study. So essentially, all the inputs, which, as Nando was mentioning before, correspond to non-flexible customers active and reactive power of flexible customers, are going to come directly from the historical data. In terms of the allocation techniques, we are going to consider 2 different allocation techniques. The first one is the equally distributed allocation technique, as we call it, which essentially assign the same flexible export limit for all customers at each instance. This means that we're going to have lower overall exports from the entire low voltage network, as we are going to be constrained by those customers that are more sensitive to voltage rises, which in general are going to be the customers that are located far from the distribution transformer. The second allocation technique corresponds to the one that we call maximized exports, which other researchers or other people has called optimal allocation. And the idea in here is that we are going to try to maximize the overall export from the low voltage network by constraining the flexible export limits from those customers that are more sensitive to voltage rises. In terms of the voltage constraints, we are going to use in terms of voltages, the statutory limits correspond to 253 volts per Australian regulation. And in terms of assets, as Nando was mentioning before, we are going to check customers' connection point, the capacity of the customer connection point, the capacity of the low voltage conductor at the head of the low voltage circuit, as well as the distribution transformer, which we approximate using the ADMD. So in here, excuse me. Sorry. So what we can see in here are the model free voltage calculations for the day of interest, which is this day of summer that I was referring before. So again, in purple, you can see the calculation done by the neural network, whereas in black, you can see the actual voltage value. So in here, I would like to stress, more than we have accurate voltage calculations, is that, for instance, around 3 a.m., around noon, and around the late afternoon, we can see that there is a high voltage headroom. So for these particular instances, what we will expect from our flexible export limits is for them to be high, because there is space for customers to export, right? Whereas we have 2 points in which we can see that we already exceed the voltage statutory limit, which is this red dashed line that we are seeing. So for these 2 points, what we will expect is that customers are not able to export at those moments because we are already exceeding the voltage value, the voltage limit. All right. So what we are presenting in here is first the result for the equally distributed allocation technique. So in this stack plot, each color represents a different flexible customer. So as I was mentioned before, we are going to get less total export from the entire low voltage network, as we are going to be constrained by those customers that are more sensitive. But more importantly is that we obtain consistent export limit. What do I mean with this? Well, we can see that, as mentioned before, around 3 a.m., around noon, and in late afternoon, we can see that there is high flexible export limits, right? This is because at those moments in time, in the actual voltage profile that we were seeing in the previous slide, we have high voltage headroom. So for instance, let me go back. So we can see here around 3 a.m., noon, and late afternoon, we see high voltage headroom. So we can observe high flexible export limits. Whereas for those 2 points in which we were already exceeding the voltage limit, we can see that customers are not allowed to export. So this is around 9:10 and around 2:30 in the afternoon. So we can see in those 2 particular points, we have our flexible export limits are 0 for everyone because we were already exceeding the voltage statutory limit. So the next plot is the maximized export or optimal allocation, in which as we constrain the flexible export limit for those customers that are more sensitive to voltage rises, we are going to obtain more total export from the entire low voltage network. So again, each color is to represent a different flexible customer. In here, again, we can see that around 3 a.m., around noon, and in late afternoon, we obtain high flexible export limits. This is because of the voltage headroom that we observe in the actual voltage profile. And again, we can see that in those particular points, in those 2 points that we were already exceeding the voltage statutory limit, we obtain 0 kilowatts as flexible export limit. So important in here is that we can say that our approach captures the underlying relationship and is able to produce larger overall export from the entire network by constraining those customers that are more sensitive. And of course, again, we are obtaining consistent export limits. Now, the big question here is that, does this work when everyone doesn't have smart meters? And why this question is important is, well, here in Victoria, we have C&I customers, commercial and industrial customers, whose data is managed by third parties. This means that it's not really available for DMSPs. And outside Victoria, we have partial smart meter deployment. Although it's going to be increased in Australia up to 2030, it's not going to be full deployment. So the idea is to test if this can work without smart meter data from our customers. So what we do to exemplify this point is that we're going to use exactly the same case that before, but we're going to consider partial smart meter data availability. Specifically, we're going to consider that the data from all three-phase customers, which are 37 for this particular case, is not available for DNSPs. This means that as we build the neural network with the per channel information of the smart meters, this is going to represent around 50% of the data. So the full case, the one that we presented before, we consider smart meter availability from all customers. And in this case, the partial smart meter data availability case, we are going to consider just 50% of the data. As you can see in the results in the lower table, we obtain, well, there is an accuracy decrease, of course, because we are not seeing all the information. But in both cases, we can obtain pretty accurate results. So for instance, in terms of average deviation, we can see that in the full case, we obtain 0.54 volts, whereas in the partial case, we obtain 0.71 volts, which is pretty accurate. So here we are presenting again these scatter plots. In the y-axis is calculated voltages, x-axis is actual voltage values. And we can see that in both cases, we are capturing the underlying relationships of the low voltage network. What does this mean? Well, this means that actually we can do this with less data. And I'm going to spoil a little bit, but in our final report, we present that this can be done with even as little as 20% of smart meter data availability. So this can be done with without 100% of smart meters. In terms of the day of interest in which we are going to calculate flexible export limits, we can see that there is an accuracy decrease. So for instance, now you can see more of the black part of this graph than before, all right? So for instance, let's consider those 2 points in which we are already exceeding the voltage statutory limits. In the first one, we are kind of capturing that we are close to the voltage statutory limit, whereas in the right part, in the right point, we are underestimating this point. So this means that the neural network is going to see that there is voltage headroom at this point, where there is actually isn't. And this is going to depend, of course, of the location and the behavior of those customers that we are not seeing. But again, we can see that we obtain accurate voltage calculation. So, lose control again. There you go. So in terms of the equally distributed allocation technique, these are the results. Again, each color is a different flexible customer. We can see that there are some difference with the case of full availability, but they are still consistent with the actual voltage profile. So for instance, in the first point in which we exceed voltage statutory limit, we can see that the flexible export limit is 0 for all customers, whereas in the second one, we do assign a small flexible export limit for all customers. And this is because what I was saying before, we are underestimating that point, and the neural network sees as there is a little bit of voltage headroom. Again, we can see that around 3 a.m., around noon, and in late afternoon, we have high flexible export limits. So this is consistent with the actual voltage profile. But of course, there are some limitations as we are not seeing all the information from the low voltage network. So in here, what we can see is the maximized export allocation technique or optimal allocation. So again, we can see that we are capturing their relationship, and we can constrain those customers that are more sensitive and obtain a larger overall total export from the entire low voltage network. But of course, there are some limitations. So for instance, in those 2 points in which before we were assigning 0 for all customers in the terms of the flexible export limit, we assign a small flexible export limit for these customers. And this is because we're not seeing the entire information. Again, at 3 a.m., noon, and late afternoon, we are assigning larger overall flexible export limit for all customers, because these are the times in the day in which we count with large voltage headrooms. So again, consistent export limits. So finally, I already spoiled a little bit about this, but you can see more details about partial smart meter data availability in our final reports. But what we can say for now is that we are going to obtain accurate voltage calculations. These are possible, even when we are considering only 20% of the smart meter data available. And of course, we're considering calculation for those customers that we can see. We cannot estimate for those customers that we are not seeing. This is not magic. And in terms of flexible export limit, well, we can obtain adequate flexible export limits, as we were seeing before, consistent with the actual voltage profile. And as I mentioned, consistency is going to depend on the location, characteristics, and behavior of those customers that we are not seeing. Finally, if DNSPs count with a transformer monitor, this can help, and we have proved that this enhance all our methodology. And with that, I will leave you with Nando to see what is next and the key remarks of this presentation.
Thank you very much, Vinny. So let's move to what's next, and we'll have some time for Q&A. I have noticed a few questions already there. So in terms of what is next, from the perspective of, okay, so what distribution companies can do with this? Well, the idea here is that we have an engine, we call it the model-free engine, right? That will replace what naturally you would normally use power flows if you really want to go into the detail of calculating the export limits in this way. So by replacing the power flows, now you have another engine that will actually calculate the corresponding voltages, and of course, the associated engine as well for the heuristics calculate as well the utilization of assets, as I was explaining earlier. Now, what you're seeing in this slide is something that looks much more complex, architecturally, in terms of software than what we were explaining. And why is this? The reality is that flexible export limits, as implemented by the likes of Sept and South Australia Power Networks, Energy Queensland is already offering this, and it will happen, through Australia for different regions. Has happened through projects, is happening now, as I was mentioning earlier. So distribution companies will have to put together platforms that allow them to not just calculate those values, even if with simplifications, but then to broadcast those values and send them either directly to the corresponding PV inverters, in this case, which is the main technology that we have in Australia, or potentially to a third party that will manage the corresponding inverters on their behalf or behalf of the customers to really follow the corresponding export limits. Now, this is not simple. It is quite an advanced platform that is required, and this is happening behind the scenes across Australia. Because according to, as I was mentioning to the ER, they will be able to offer this. But for you to offer it as a company, then that means that the platforms are already in place. However, the model-free engine can be just a building block that enters this ecosystem. Now, of course, in our case, there's an offline component that requires the production of the corresponding neural network. But then once it is produced, after a few minutes or hours, depending on how big it is, the corresponding neighborhood, then it is ready to be used for online purposes. So this is just to give you a sense of, this is just a building block into a much bigger thing that the distribution companies have now to deal with. And it's quite exciting. This is unique in the world, actually, as a matter of fact, and will help us managing all the challenges of not just photovoltaics, but other challenges that we'll have with different technologies in the future. Now, this is not just about flexible export limits. I believe, we believe strongly that these model-free applications are many. Here, one example of PV hosting capacity. So this is with recent data from a distribution company. And what we have here is T1, T2, two distribution transformers, two little neighborhoods, right? With a bunch of customers. And well, some of them do have solar photovoltaics, but the big question, for distribution companies, not just in Australia, but in many places around the world is, okay, how much this neighborhood can have in terms of more photovoltaics, right? That's the typical question. And what they normally do, they just use the transformer capacity as a proxy of what can actually be handled there. But the reality is that that is a very simple approximation that, of course, as you would expect, as any approximation, can lead to many errors. Nonetheless, well, that's something that can be done right now, but it is possible to do it better. So how can we answer this? How much more solar PV question we can have? Well, here's the answer. So for transformer one, if you have the model-free approach, we can tell you, well, the additional solar PV that you can have is around 350 kVA, all right? And the main problem is voltage rise. However, if you went just for the simple approach of just using the transformer capacity, well, you will say that it is more than 400 kVA in total of PV that you can have, because your only problem or your only constraint that you're considering is thermal. And here you can see a significant overestimation. So if you, as a distribution company, go through the simple approach, which is okay, we need to make decisions today with the tools that we have. But the problem is that it can create some issues down the road if all the customers really install up to that value. Now, that same thing we can see in transformer number 2, where there's an overestimation because the voltage rise issues are not being captured by simple approaches, whereas the model-free approach can actually do that for you. All right, so let me get into the key remarks, and we have some time for questions as well. So I wanted to summarize everything that has been done. Not everything that we have done in these 2 years has been presented in these 40 to 45 minutes. Apologies, that's the nature of a webinar. Otherwise, it would be just way too much information. And given that we have all the information public available, we encourage you to go to our previous webinars, reports, papers, or just contact us as well anyways. So I guess that the main message that I want to give, not just to the power community, but in general to people, is that, well, a model-free future is possible. We can really extract much more insights from smart meters than we thought we could. And this is fascinating. I mean, at least I find it fascinating, to be very serious. It's really interesting. This is not to say that we do not need electrical models, by the way. We are not advocating for this. What we believe is that it will take some time to get the electrical models right. And even if you get it right, well, you have an alternative that is even much faster, or can be used to help to check things, or issues with electrical models even much faster. So there are many opportunities here. Now, this technique, if implemented by distribution companies, has the potential to remove time and cost associated with the production of electrical models. It can work with partial smart meter data availability. And this is very important because as much as we have so many smart meters here in Victoria, well, all houses have smart meters. Outside Victoria, that's not the case. And around the world as well, the smart meter deployment is continuing. And there are many places that don't have such a smart meter data availability, such as Victoria. So we can do this with partial availability, and that's great. We just need 3 weeks. This is not about a data-hungry approach. It was from the very beginning designed to use just a little data, not just because it's just little data and computing power will be less. It's not that. It's extremely important to understand power systems when applying these techniques. Low voltage networks can change topologically. A big house can become 3 small houses. A transformer can be upgraded, the conductors can be upgraded, or can be extended. A street can become a longer street just because there was a development. That creates a topological change in the low voltage. Now, it doesn't happen every week. It doesn't happen every month, but it can happen once a year, depending on the areas. So if we go for a lot of data, a year data, like typical data-hungry techniques, well, we won't be able to capture the physics because it will be different networks that are there in the data. So by doing smaller amounts of data, we can ensure that the network is the network that we're looking at and not a mix of networks because there was a topology change in the middle. Now, this also ensures that it is very quick to produce a corresponding neural network. Now, we have also demonstrated, not in this webinar, but go to our reports, that the same neural network can be used for multiple months without updates, of course, provided that there's no topological changes. And we have also demonstrated that the neural network can be even better than the best electrical models that you can produce. Because the electrical models, at the end of the day, 3-phase electrical models, they don't cater for grounding. They don't cater for all the joints that we have. The neutral is modeled, but it's still, it's not necessarily exactly as it is in reality. There are many assumptions even in our electrical models, but the data captures everything, the real data. So we have demonstrated that in previous webinars as well, but we encourage you to go there. Now, there are multiple applications that can be extracted from this. We're just scratching the surface. So flexible export limits or operating envelopes, the obvious ones. This project was about that. We have also demonstrated connection requests and hosting capacity. Do please go to our reports. But there are many things as well that are very exciting. What about hybrid state estimation? Today, state estimation is just limited to what we call high voltage here in Australia. Think of 22 kV lines, right? Medium voltage international. What if we extend that with the low voltage? And then we can estimate what is happening, at the very end, at the household level. We can do a hybrid. What about hybrid planning? Also mixing our electrical models of the high voltage that most companies around the world have, or medium voltage, if you want to use that international terminology, combining with the LV model free. So there are many possibilities, and we're scratching the surface. And this particular project, this 2-year project funded by C4Net and the different distribution companies of Victoria, really allow us to demonstrate this and to produce this. And we're very thankful for this opportunity. Now, this also allows us to bring these ideas to the market, and we're in the process of doing that. The University of Melbourne was very kind to award us a proof of concept fund, and we're developing the software. It's almost ready, and we are doing this co-design with leading electricity distributor, Osnet Services, that has been a partner throughout many projects, thanks Osnet. And we are in a strategic partnership with a very key player in the smart meter domain, which is Future Grid. There's a company that manages smart meter data for many distribution companies, not just in Australia, but around the world. So want to learn more or contact us? Well, mine is there. But before we finish, just let you know that we will make the slides available. There are lots of links, lots of publications for you to go to the different details. I would like to thank again, Vinny, you did a fantastic job. Thank you very much for all your hard work. Tansu, Chris, thank you very much for your advice. C4Net, James, Chica, Sanas, thank you very much for all your hard work throughout this year and last year as well. John, part of HostNet Services, well, he used to be part of HostNet Services. He was throughout all our meetings, but end of last year, he retired, but John still, thank you very much. Toby, United Energy, Dan, Gemina, they were very involved as well throughout the project. Thank you very much for your support. Kenneth, more recently from HostNet Services, Chris and Roche from United Energy, thank you very much for your support. And finally, the University of Melbourne, Michael, Angela, Shang, and the Melbourne Energy Institute, thank you very much for all the hard work in helping us with this project. And with that, well, we have a few minutes for Q&A. Chica, would you like to mention anything, or shall I just go straight to the Q&A?
No, feel free to go straight to the Q&A. There's several great questions in there already.
Excellent. So I'm going to go relatively quick through some of the questions because I already went through them while Vinny was actually presenting. So, well, the first question from an anonymous attendee confused about imports and exports. So exports is when we inject power to the grid. So our photovoltaics, when there's a lot of sun, they generate power, but if we're not at home, we only have our fridge, well, the excess power goes back to the grid. That's what we call an export. And the normal situation when you actually just use electricity from the grid, that's an import. Daniel is asking, does the report include analysis of the geographical prevalence of export limits? No. That's not what this project is about. But that information actually is a little bit tricky as well to find. In general, 5 kilowatts is the standard offer from distribution companies in Australia, single phase. If you are in a SWER network, meaning a rural, some companies do 3.5 as a standard. But again, it all depends on where exactly you are, because the distribution companies will tell you if you're a neighborhood array with photovoltaics, it's very likely that the value will go even lower and lower. Now, interestingly, Daniel as well and everyone, well, the thing is that because of the flexible exports, it's something that will be I wouldn't say push, but will be promoted by distribution companies because it's the best way of managing the pole-side wire and avoiding really excessive investment in more copper, right? And that's what we want. We want to avoid that investment that is higher electricity prices, and well, also, you know, that creates a lot of the embedded carbon, right? So it's not great for the environment. So if we can do the most with existing infrastructure, why not? So the flexible export limits is a reality in Australia, and because of that, well, it is very likely what we're going to see is that the export limits the standard offers are going to be even smaller. So let's brace for that. Anonymous attendees asking two-way pricing. Yeah, that pricing, I'm not involved with pricing here. This is all about technical things. Pricing is another very interesting thing, but it is not associated to this project. Now, anonymous attendees asking, I can understand you can simulation different operating conditions, how you can compare the two different operating conditions. Is there any way to get optimal? So what we do is similar with power flows. Well, how would you do? You explore one level of export limits. Let's suppose all your flexible customers export one, right? Your non-flexible will have the demand that you're estimating for the moment in time. And then everyone with 1 kilowatt of export, no problems. Then you go to 2, and then to 3, and then you find what is the value that all for the equally distributed can go up to. So that's how you compare. And then you always check with voltages and the assets as well. Now, for the other technique, what we call the maximize exports, well, I mean, it's a heuristic that is slightly different, but the principle is always check for each case that you explore. Is there any way get optimal suggestion coming from model-free simulations? Well, the optimal one, I would say, is the maximize one, right? So that's the one that makes the most for the whole community in terms of the total exports. Now, you will be affecting someone, the house at the very end of the street, but that's just life. So we will need to, I mean, this is not us telling the distribution companies or the regulator what is the best way. That's something that needs to be decided by the different stakeholders. Now, Farad is asking how robust the neural network approach to rapidly changing grid topology. Now, like a power flow, if the topology changes, your power flow is rubbish. Same thing with the neural network, so you need to update it. Now, the advantage of the neural network is that you can actually sense if, you can track if the voltages are way off, right? Because you have the historical data coming all the time, every day, so you can check. And if they are significantly way off, you can flag that perhaps there has been a topological change, and then, well, you need to retrain the neural network. But the same thing as the power flow, my friend, if your topology has changed and your electrical model hasn't been updated, what happens? Everything goes to the bin, right? Now, in terms of new technologies, new technology behind the meter doesn't change the topology. So the neural network continues to apply. But refreshing things is good because, of course, new technology will do more exports or more imports. So that refresh would be appropriate. And that's what we suggest as well with the neural networks, to refresh it every few months. But anything behind the meter is not a topological change. Anonymous attendee is asking, have you considered temperature dependencies? Nope. And in general, well, because of the assets, I mean, there's a lot of, let's say, headroom with the assets. But well, in general, we have not considered the equipment loading associated with the temperature. For the calculated versus actual graph, what is causing the straight diagonal line? Oh, you're referring to, I think that we can go to this plot here, this one here, I believe, the full availability. Well, it is what it is. That's what I would call it. But Vinny, do you have any comments for that particular little cluster there?
No, probably. My guess is that it's erroneous measurement in a row that were not filtered by the data processing.
Yeah, but I guess that the most important thing is to focus on how many points you actually have in the identity line. And well, I'm here with slide 35 that also shows the partial availability, for the partial availability as well. So yeah, the answer is we have guesses, informed guesses, mistakes or errors in the data, but not an actual answer beyond that. Sorry about that. Daniel's asking, cluster, yeah, it's the same thing as well. Mosen is asking, can you please elaborate more on the ratio of calculated export limits versus customer PV capacity? Do you have any data that curtailment rate in this case study? No, this is not curtailment, Mosen. This is all about the export limit, not how much people will be curtailed. The curtailment can be an assessment based on what actually happened or what could happen depending on the irradiance, the typical irradiance, etc. So that can be done because, well, we have all the numbers there. But the idea here was to demonstrate that the export limits can actually be calculated with a pretty good accuracy, because the voltages are calculated also with a pretty good accuracy. But the corresponding curtailment that will happen can be calculated afterwards, or simultaneously, actually, as a matter of fact, because the moment you have the export limits, you can estimate, what would be the corresponding curtailment. So that can be done, but that hasn't been included in this particular webinar and the reports. But yes, we are interested in doing that as well, to be honest. Anonymous attendee is asking, first of all, thank you for the presentation. Oh, thanks. We're grateful to clarify these questions. Slide 25. Let me just go super quick. The figures refer to load profiles or just one? No, these are all the customers. These are all the customers that we use for the Gemini app. Yeah, they are all one on top of the other. And the idea was just to show you the spread of the data. So we can see the photovoltaics, the negative active power, the demand. We can see the reactive power that is not just absorbing as we traditionally think people do. No, actually we have a lot of capacitiveness as well. So injecting reactive power to the grid, and the voltage is all over the place, right? And in some cases, a little bit beyond what it should be. But I mean, that is a big challenge that distribution companies have as well. Anyways, so I hope that answers slide 25. Slide 26. What is the unit of RMSE? It doesn't have units. It's the root mean square error. Have you normalized output voltages? No, we don't normalize the output voltages. The output voltages are the voltages. I mean, within the neural network, there's a normalization that happens, right? So I'm not going to go into the details, but the actual voltages that we calculate are the voltages in the units in volts, right? Slide 37. All right. The figure represents the aggregated real power PV cells could be injected over a day. Well, not the PV. The idea of the export limits is for something that could happen at night as well. It could be a battery, and suddenly the market requires exports, right? Well, at midnight wouldn't happen, but still you can calculate it, right? So we're calculating it, and that's the idea, right? So of course, during the day it's associated mostly to PV indeed, but it's not just about PV. Export limits, and particularly in the future, perhaps import limits, when we have to manage electric vehicles, is really associated mostly to certain technologies, but it's just to allow other technologies to do other things as well throughout the day. Now, of course, if it is PV, and then we're looking here that people will not export more than, I don't know what it is, the value. Let's pick at 2 p.m. The value is approximately, I don't know, I think it looks like, I don't know, help me here, Vinny, like 7 kilowatts, something like that, right? 6, something like that.
Distributed, yes, I will say something like that.
Yeah, something like that. So like at 2 p.m., it looks like around, for many of them, it's around 6 kilowatts. So if everyone had 5 kilowatts of PVs, then actually they can, if it is fully a clear sky day, super sunny, they could eventually be able to export everything. But in reality, well, perhaps, this export limit is even much higher than what it can do as well, all right? So I hope that answers your question there. Heather is asking, how do you imagine this works in practice? The neural network model recreated every 3 weeks? No, Heather. So the idea is that this is refreshed every quarter, perhaps, or if a topological change has been detected. But in general, we have proven that the neural network can actually work on its own for months, and this is all documented. Every 3 weeks, no chance. It has to be every few months, if at all. Russell, all right. Thanks for attending. Heather is asking, what proportion of solar power are you recovering? That was pretty limited. Well, that's a question related to what Mohsen was saying, and we haven't calculated that. That's an interesting question. We have all the data to calculate that, but no, the focus of this webinar was to show that we can calculate the export limits. Now, what it means at the end, for the end user, and how much more they can do or how much less they are going to be doing because of this new technique, that's something that is totally relevant. And I do appreciate the question, but no, we are not showing those details here and not in the reports. It's not the scope of this project, but we might do it in the near future because it's an interesting question. Thanks. Other question from Heather. Another approach might be to measure the voltage locally and respond to what you think the difference might be. Well, yeah, of course. That's another approach, Heather. I totally get it. But the question is, which one is more accurate, right? I think that ours is more accurate, but you need to do the corresponding comparison. Why do you choose a neural network among the large model techniques offered by machine learning? We are exploring other techniques, Wilson. We chose neural networks because it was very promising with our initial studies. So we're talking about 3 years ago when we started this. The project is 2 years ago, but the initial studies started 3 years ago. So at that stage, it was very promising. So something very important as well, Wilson, this is not about having excellent results with test data. The test data is just the beginning of using machine learning techniques. You need to understand that then you are forcing the neural network or any machine learning technique to extrapolate beyond what they are used to. And this is where the neural network became very interesting for us because other techniques were not necessarily that good for extrapolation. So it doesn't stop saying my neural network or my machine learning technique here is awesome for the test case, which is very similar data to the training case anyways. The point is to put it to the real test, which is hosting capacity, operating envelopes, values that the neural network hasn't seen or the machine learning hasn't seen. And some machine learning techniques are quite rubbish on extrapolation.
Actually, a point on that is that, for instance, you could use linear regression and you can get pretty decent voltage calculations, but as soon as you start to extrapolate, it's going to fail.
Exactly.
It's going to be way off.
Thanks for that, Vinny. And so Wilson, that's an interesting point, right? And this is why we need to be engineers here, not just computer scientists. What is the problem in hand here? It's not having the best RMSE for the test with the data. It's about having something that works the moment that we push the boundaries of it. And these are values that are not being seen at all, right? Hosting capacity is about a planning assessment, something that might not happen next week, might happen in years, but you want to do it. And that means that there's no data that you can train from, right? So that is an important point. Thanks, Vinny. There's anonymous. What is the rule of Q? Oh, right. I do not have much Q. It can be ignored. No. Rectifier can never be ignored, my friend. No. If you are not a power engineer, I can accept that from your side. If you are a power engineer, no, my friend. Go back to the basics. Rectifier is very important. Otherwise, you cannot have adequate voltage calculations. Again, like a power flow, you remove Q, you are going to have rubbish values, all right? So Q is very important. Now, it's small, sure, but it still does matter. And in all, despite the fact that we haven't really emphasized this, in everything that we are doing, Q is very important there. If we remove Q, the values that you would have are not gonna be good. Simple as that, right? If you do a neural network just with P without the Q, unfortunately, is going to be quite bad. And you cannot forget the fact that also we have now reactive power effects from the photovoltaic. So they play a role, and we need to learn from that as well. So the volt var control, if you are aware. So Q is very important. And also the fact that Q is not just positive as in inductive, absorbing from the grid, it's also injecting. And that needs to be captured as well. So that's why it is also very, very important. Wilson, how will our approach behave with weakly mesh networks? We haven't tested it, Wilson, but in low voltage networks, most in the world, they are rated, so it doesn't matter. Arno, how will the model deal with seasonal variation? Well, Arno, in this case, well, as I was mentioning, not in this webinar, the previous webinar, we demonstrated this, there's full reports. It lasts for months, provided that there are no topological changes. However, our recommendation is that, after a few months, you refresh the network, because if you have more data of the photovoltaics, people install photovoltaics or electric vehicles, that newer data will make the neural network better, because again, it's about extrapolation, and the closer that you get to the extrapolation with the original data, the better. So seasonal variation doesn't really affect. But we recommend this neural network to be refreshed every few months.
We have done detailed assessment of seasonality over the.
Yeah, absolutely. And this is in some of our reports, indeed. Anonymous, may I ask how to the recorded videos? Oh, you will receive an email given that you have registered, and you can also go to our website, and then you will see all the webinars there. What can be done to make it real time? This is real time. I mean, the offline part of the creation of the neural network, of course, is offline. You need to process the data, create the neural network, but then once it is produced, it can be done in real time. It's like a real-time state estimation using electrical models, or any calculation using electrical models, the same thing. The moment that you have produced your neural network, you just implement it in real time. Now, as I was trying to mention with the architecture that I presented super quickly in just one slide, this is a big challenge for distribution companies, not just in Australia, but others around the world. This is not simple, and they are putting things together very, very well, and it's admirable what they are doing. But it is a very complex process, but they are getting there, all right? So we are just providing a little box that hopefully will help them. Richard is asking, does your model include solar inverters going to reactive power? Yeah, well, it's not that our model, so the photovoltaics were present as well in the data that we use, because it's not just Gemini. Sub-B is just one case study. We had multiple substations, distribution transformers, and they included as well photovoltaics that had already the volt watt and the volt var. So it's all captured by the smart meter, because they are capturing the P, Q, and the V, right? So yes, the neural network captures all the behavior of the photovoltaics. Now, where the question is, are you considering the photovoltaics effects in terms of the volt watt control, volt var control in the calculation of the flexible exports? In this particular project, no. For simplicity, we did not, but it can be included as well. Is there a way to see the sections conductor reaching the constraint? Well, just the head of the LV circuits can be checked, because we know what are the sizes of those conductors, and we can just use as a proxy. Now, why is it a proxy? Because what we do when designing the low voltage networks is, we actually, in general, distribution networks, we do tapering, right? So which means we start from a larger conductor to smaller and smaller, because we have less houses. So if the head part, is actually okay, we can assume that the rest is okay. Is the Python code developed for the project openly available? Nope. Will it be commercialized by Goldmine? Yeah, the IP is owned by the University of Melbourne, and yes, it is being commercialized by Goldmine. That's the whole point of the proof of concept. If we prove the concept, yes, and we're in the process. Fingers crossed. Craig is asking, shouldn't it be better to fit envelopes allow greater PV penetration than the current numeric determination? Well, I mean, Craig, well, the thing is that you can use the whole technique to do hosting capacity, right? And then define how much you can have. You can use flexible exports to allow more exports. I mean, at the end of it, it's a technique to quantify things related to voltages and assets. How you want to use it is another story. In this case, we're just using the application of flexible export limits in this particular webinar, but there are many other applications. Heather is asking, is voltage the only limit you need to worry about? Well, when it comes to photovoltaics, pretty much in most cases, the answer is yes. And the distribution companies are very aware of this. However, you need to also check the transformer and the conductors, and we are doing that in this case as well. Anonymous is asking, were the full LV networks used in the study? Oh no, we use more than full LV networks. There are 4 circuits in the substation B of Gemina, which is one case study, but we use multiple transformers here. And they were not chosen at random. They were chosen in collaboration with Gemina, United Energy, and Wasnet Services, because the idea was that they were making sure that this data, actually they gave us data for around a year, because first we didn't know how much data we could use and how much data we would need it. At the end was 3 weeks, right? But we didn't know this 3 years ago. We were hoping, but we didn't know. So we asked for more data, and the idea was that they were checking that all the smart meters were there associated with the same transformer, and that there were no topological changes. And just those 2 considerations is not that simple. And again, thank you very much, Gemina, United Energy, and Wasnet for the hard work in putting the data together for us.
To be specific, there we use 8 low voltage networks with more than 690 customers.
Correct, and all the results and the data are in our reports. The analysis on what happens for those customers that are not well modeled by the neural network, worst case scenario, more than 3 volts. What happens to the customers that are not well modeled by? Well, I mean, so the thing is that this is not a perfect thing, right? And then there will be, you might have noticed that the maximum voltages can be, the errors can be around 10 volts in some cases, but those happen very, very little times. So there are things that can be done to improve that, and we are working on that, but that's beyond the scope of this project. But in general, I would like to highlight the average deviation, which means most of the time, there's an error of around 1 volt, and that's pretty awesome considering that you don't have the low voltage electrical model. The neural network retrain on data, including previous neural network informed envelopes and force. That's a very good point, Craig. Yeah, of course, because if you put operating envelope in force or export limits, and then you retrain that with that exposure, the neural network will get better, because if some people did use the export limits to those points, it means that you will have newer data, right? So, well spotted. That is the idea, but no, in the case of what we did in this particular project, no. But yes, what can actually be done to improve it? You're absolutely right. You're spot on. Scott, can the employee streamline the connection agreement process for large generation systems? Well, it depends on what we define of large, but it certainly is not residential. So everything that we have done is really for residential purposes. We do believe there's a scope for doing this for high voltage networks or medium voltage networks, as some people call it. So 22 kV, for instance, and large systems like hundreds of kilowatts could actually be included. But the amount of data that is needed is quite significant. So we are trying to come up with some options for that, but there are some opportunities there, Scott. Thank you for the question. Here's asking, yours might be more accurate, but I won't respond to changes in real time. Oh, no, it does respond to changes in real time as well, this one, Heather, because the whole point is that neural network already captured that physics, so it is responding to anything, any case that you want. Taruski is asking, was the voltage actual versus predicted comparison for all customers? Well, yes. So what we put there it was for all the customers that were considered the neural network. So yes, all the comparisons that you see, for instance, those plots here, yes, is all the customers that are there. So the area, the black area, shows the maximum values of all the customers simultaneously and the minimum, just for you to see kind of that envelope, of the range of voltages for each time step. And of course,
the question is related to the scatter plots, and yes, it's all customers at all instances. Yes.
All right, if it is scatter plots, yes, as well. But it's the same thing as here, right?
Yeah.
Okay. Matt, and then we're getting to the end, and then we will finish this. How critical is the time synchronization of the data from the smart meters? Oh, it's very critical, Matt. Very critical. But I mean, in our experience, yeah, I mean, let's start from the basics. Smart meters, right? So supposedly they are time stamped, right? But time stamped doesn't necessarily mean that it's precisely. They are not phase or measurement units, right? So there might be a little bit of, when they say, okay, the snapshot is not necessarily exactly, to the, millisecond, what they are taking, everyone at 2 p.m. That doesn't mean there's a snapshot. It's exactly, at 2 p.m. Might be a few seconds here, a few seconds there, or in between the smart meters. But that is not significant. The neural network can actually capture the physics still with that. So that's good news, I would say, which is great. And Gary, finally, you are the last one. Can you use transformer monitors instead of AMI data? No, what we have demonstrated actually, Gary, and you can go to our reports, is that if you use, in addition to smart meter data, transformer monitors, then you get an even better neural network. A really, really good, neural network. And that's what I was trying to mention in one of the slides, that if you have transformer monitoring, you can improve this massively. So if you have that, yes. Now, instead, no. Yes, with transformer data, you cannot assess what is happening at the end of the street. You need smart meter data. And with that, thank you very much, everyone, for your questions. I really appreciate it. Thank you very much for joining us today. Vinny, again, thank you very, very much for all your hard work. And Chica, back to you to finalize.
Thanks very much, Nando. Chica's unfortunately had to head off. So on behalf of C4Net, we thank Nando and we thank Vinny very much for their presentation today. And for all of the participants who contributed questions or listened in on the presentation, we thank you as well. We're going to close the meeting now. So we wish everyone a happy afternoon. And thanks again for your time.
Thank you very much. Bye-bye.